Hi folks, I know we've been a little bit rushed heading into our assessment task for probability this semester. So I thought for our last lesson I'd actually make a video of the 3 examples in the lesson so that you guys can watch them in advance if you want to try and work ahead and be a little bit more prepared for the test. So this first example is straight from the lesson slides. It's on slide 46. It's the engage activity for the lesson. And the question says a 6-sided dice is rolled 3 times. Let X equal rolling a 6. So X is the event of rolling a 6 on the dice. We want to start by finding the probability of rolling a 6. So I could go to the methods that we've been discussing previously and create up a tree diagram, and I could put 6 branches on each end of my tree, and my tree diagram is going to get very big very quickly. So then I might sort of think, well, let's be a little bit more efficient, and I'm actually just going to make my tree diagram with the probability of getting a 6 and the probability of not getting a 6. And then this is 1/6 and this is 5/6. Badly drawn fractions there, but you get the idea. And what I want to do in this video though is actually work even more efficiently than the tree diagram. So we're going to look at some different techniques. But for this problem, let's actually just start with the basics. If we want to find the probability of rolling 3 6s, that's pretty straightforward. We can get, I'm going to use S for 6. We can get a 6, and then another 6. And if we got 3 6s, each roll is independent, so I can just simply do 1/6 times 1/6 times 1/6, or even better, 1/6 to the power of 3, which in this case is 1 out of 216. Perfect. So now let's go to the next part of the problem, part B. It said find the probability of getting 0 6s. So find the probability of 0 6s. All right, so same idea as what we just did. We want to have not a 6, not a 6, not a 6. Again, these events are independent, and the probability of getting not a 6 is 5/6 times 5/6 times 5/6, which is 125 over 216. Now, if we move to part C, though, part C says find the probability of rolling 1/6. Find the probability of rolling 1/6. So when I start thinking about this, there's actually 3 ways I could get 1/6. So I could have a 6 and then 2 not 6s. I could have a not 6, then a 6, then a not 6. So we've got to start thinking about all of the combinations that we could possibly have. And then I could have not 6, and a 6 as my third one. So if we work through these combinations, if I get a 6, that's a 1 in 6 chance. If I get not 6 on my second roll, that's 5/6. And then on the third roll, not 6 again. So there's a 5/6 chance of that occurring. And I'm going to write this in index notation because it'll lead to what I discuss in the rest of this lesson, which when I calculate that is 25 216ths. Now what's interesting in these next 2 examples is although the order has changed, so we see the fractions happening in a different order, the actual numbers haven't changed. And that's really easy to see when we write that in index notation, that the numbers are exactly the same, even though the combination's different. And I'll continue the last one as well, just to show you how that works. So we've got 5/6 times 5/6 times 1/6, which gives me 1/6 times, oops, I forgot the squared there, 5/6 squared on the second one. And because all of these combinations give me the possibility of rolling 1/6, we need to add up all of these answers at the end. But rather than add them, because they're exactly the same, we're going to use repeated addition. We just use multiplication. So we're going to do 3 times 25 over 216. Or where did that come from? 3 times 1/6 times 5/6 squared. All right. So this idea of where we're going, I'll talk a little bit more about as we go forwards. But the bottom line is the total probability for getting 1/6 is, so I'll write this as the probability for 1/6 is equal to the probability that x is equal to 1. And then that's equal to, oops, can't write numbers, 75 216ths. Where did that come from? Right over here, if I do that calculation. Okay, so as we built in this problem, what we're starting to consider is how many different combinations of 1/6 there is. And I've deliberately used that word combination. You could say, how many ways can I select one of the roles to be a 6 and the other 2 roles to be a not 6? So I've got those words combination and selections. So hopefully you're starting to put that together with what we did in semester 1 when we did combinatorics. All right, last part of this question, find the probability of rolling 2 6s. So same deal again. Oops, I don't know why I put an F there. Brain's a bit done, it's late in the evening. So probability of getting 2 6s. So we want x to be equal to 2 because x was rolling a 6. So we want 2 6s. Same thing again, we can go through all of the combinations. So I could have 6, 6, not 6, 6, not 6, 6. Or we could have not 6, 6, 6. And for all 3 of these combinations, it is going to be equal to 1/6 times 1/6 times 5/6. Because these ones here, they're when I get a 6, that's when I get a 6, this is when I get not 6. And if I change the order, it's going to be exactly the same. So, index notation, 1/6 squared times 5/6. And then how many different combinations do I have? I've got 3 different combinations for doing that. So to work out the probability of getting 2 6s, I've got 3 times 1/6 squared, which is 3 times 1 on 36 times 5/6, which equals 15 216. All right, so we have now all of the possibilities. So where this is leading to, this lesson's about probability distribution tables. So I can now put this into what we call a probability distribution table. And all that is a fancy way of saying, I'm going to draw up a table that shows all of these possibilities. So let's forget the notation for a moment and let's just build my table. Going a little bit slowly at the moment to try and keep it nice and neat, and my cells aren't all the same size, but they're close enough. So if I wanted to get 0 6s, then there was a 1 in, oops, that's not correct. 0 6s was a 125 in 216 chance. 3 6s was a 1 in 216 chance. Okay, so this should have been, let's correct this, probability of getting 0 6s is 125 out of 216. Probability of getting 3 6s was 1 out of 216. Probability of getting 1 6 was 75 out of 216. And the probability of getting 2 6s was 15 out of 216. And what we'll notice is that all of these probabilities down the bottom here, 1, 2, 3, 4, when we add them all up, the sum of these is equal to 1. And as it should be, because the total probability always adds up to 1. We've seen that in our previous examples. So the only thing really new that we've got to learn for this table is the notation. So we're going to call these values x. These are the possible values that you could get, the possible number of 6s that you could get when you roll a dice 3 times. And the bottom here, this is the probability that rolling a 6 is equal to whatever the number is in the top table. So this was my probability of rolling a 6 x times, where x is 0, 1, 2, and 3. Okay, so they're probability distribution tables. We're trying to be a little bit more efficient with how we calculate those numbers, and we're starting to think about combinations for arranging the possibilities. Which brings us to the second example. So, example 2, which I think was on slide 48. So it's the same idea, except now in slide 48 it says I've still got x is the event of rolling a 6. But now we're going to roll a dice 5 times. Draw a probability distribution table. Spelled probability wrong. Okay, so what I'm going to try and do is use a shortcut. I want to be as efficient as possible. And what I'm going to do to help create this problem is I'm going to start thinking about how we got our answers to the first part. So let's come back up here and let's just look at this point here, the probability of getting 2 6s. So when I did that, to save time, I just worked out how many combinations. I'll just highlight that there. That's the number of combinations. This is the number of ways I can arrange. Sorry, not arrange. This is the number of ways I can select 2 6s and 1 not 6. So this is a combination. And then this one here, this was the probability of getting a 6. And this one was the probability of getting not a 6. All right. And finally, we had to square it because we needed 2 of them. And then there's a little power of 1 here, which I haven't written because there's only 1 not 6. So let's kind of use that idea for our next example. Let's start with working out what is the probability that x, the number of 6s, is equal to 0. So we need there to be no 6s. Well, this one's easy. So I'm just going to say, how many ways can I get 0 6s? There's only one way that you can get 0 6s. And that's to get anything but a 6 times by. I don't want to get any 6s, so the probability of not getting a 6 is 1/6 to the power of 0. And everything else is 5/6, and we need to get 5 of them. So the short version of this is to jump straight to this step here. This is the combinations. This is the probability of getting a 6 and how many 6s that I want. This is the probability of not getting a 6 and how many not 6s I want. And when you do that on the calculator, because let's not do it by hand at this point in time, you're going to get an answer that is, I've got to try and remember now, 3,100 and, start that again. 3,125 over 7,776. Now I'm going by memory, so sorry if that's wrong. Okay, let's look at the second combination. If we want to get 1 6, well, let's just make a little note over down below here. What does that look like? So it would be a 6 not 6, not 6, not 6, not 6. Then we'd want a not 6, a 6, not 6, not 6, not 6. It's going to take me ages to write down all of these combinations, and the chances that I miss one is pretty high. So what could I do instead? This is where I can use the combinatorics that I learned in semester 1. So I'm going to do NCR. And you might remember NCR is n factorial divided by r factorial, n minus r factorial. And you can use your calculator to do that. There's other notation that also looks like this. So it's like a fraction in brackets, but we don't draw the vinculum line. So don't draw that line there in. Undo that, we don't want that line. Okay, so for our problem, we have 5 tosses of the coin, and we want to choose one of them to be a 6. And the probability of getting a 6 is 1/6, so I want one of them. And the probability of not getting a 6 is 5/6, and I need 4 of them. So my shortcut, my most efficient way, if I want to find out the probability that the number of 6s is 1, I can do the combinations multiplied by the probability of getting 1 6 multiplied by the probability of getting 4 not 6s. If you chuck this onto your calculator, again, I'm going by memory. Hopefully I've remembered it correctly. 1,250 out of 7,776. How did I get there? Actually, I have a feeling that I got that wrong. Let me do the quick calculation instead. 5C1 is equal to 5 times 1/6 times 625 over, can't remember, I think 6 times 6 times 6. I've actually got it up here in my earlier notes. So let's me try and find 1,296. So it then equals 3,125 over 7,776. Or does it? Yes, I think it does. That looks all right. Okay, if I've got the numbers slightly wrong, we'll get over it. So let's just see this a couple more times. If I want to have 2 6s, how do I do it? Well, from the 5 rolls, I want to choose 2 of them to be 6s. And then the probability of getting a 6 is 1/6, and I need that to happen twice. The probability of getting not a 6 is 5/6, and I need that to happen 3 times. If you put that onto your calculator, this time we're going to get 10 times 1 over 36 times by 125 over 216, which equals 1,250 over 7,776. And we can actually use this method to keep going to get all of our possibilities. All right, so really quickly, PR x equals 3, that's getting 3 6s. So from the 5, we need to choose 3 of them to be 6s. So I need 1/6 to the power of 3 and 5/6 to the power of 2. When you do that, you get 125. I'll try and keep my workings a little bit better this time. The first time I did this video, it was woeful. 125 over 776. Probability of getting 4 6s. So from the 5 rolls, we need to choose 4 of them to be 6s, times by 1/6 to the power of 4, times by 5/6 to the power of 1, which is 5 times 1 over 1,296 times by 5 over 6, which is 25 over 7,776. And then the last one, probability x equals 5. So from the 5 items, I want to choose 5 of them to be 6s. So I need 1/6 to the power of 5, and I need 5/6 to the power of 0, which is 1 over 7,776. All right, so this is our shortcut for jumping straight to each of those probabilities. And I can put that in a probability distribution table. So let's try not to make this too ugly, but also I don't want you to be watching a video of me making a table look perfect. So I'm just going to bang it out here pretty quickly. So we want 0, 1, 2, 3, 4, or 5 sixes. And these are my X values. They're the possible number of sixes that I can get. And this is the probability that of rolling a 6 being equal to whatever X is. And all of my numbers here, we had 1 over 7,776. We had 25 over 7,776. 125 over 7,776. 3,000, can't remember, 3,125 over 7,776. I think I missed one there. I did. That one was 1,250 and 3,125, 7,776. 3,125 over 7,776. And if I add all of those together, it should get a sum equal to 1. It's possible that I've made a mistake with one of those numbers because I was kind of going by memory. I've made this video twice now. All right. Example 3. Now, example 3 changes a little bit. This example is on slide 51. And it says, Denny must pass through 4 sets of traffic lights as he travels to school each day. Let X equal the number of traffic lights. So X equals number of traffic lights. The following probability distribution table shows a probability that Denny stops at 0, 1, 2, 3, or 4 traffic lights. And then you get a table that looks like this. And again, I don't want to spend too long having you guys watch me draw a table. So sorry if this doesn't look pretty. But we're just going to bang it out quickly. So I've got the probability that the number of traffic lights is equal to X, 0.1, P, 2P, P, 0.1. Okay, and then part A says, find the value of P. All right, so in here, this is where we've got to remember that the sum of the probabilities must equal 1. So we're going to go straight to that to solve this problem. So we want this one, plus this one, plus this one, plus this one, plus this one, have to get a total of 1. So 0.1 plus P plus 2P plus P plus 0.1 have to equal 1. Now, if this was a calculator problem, you could just type that into your calculator with solve. But because it's a relatively easy expression, we're going to solve it by hand. So it's 4p plus 0.2 equals 1. So 4p equals 0.8 and p equals 0.2. Perfect. So let's actually just go straight up to my table here and let's replace this p with 0.2. The second one here, it's 2p. So that's got to be 2 times 0.2, 0.4. This one, 0.2 again. And I'm just going to get rid of my highlighting from before because it's in the way. Awesome. Part B. Part B says find the probability that x is greater than 1 and less than or equal to 4. So what this is asking me is what is the probability that the number of lights that Denny crosses is greater than 1 and less than or equal to 4. And because it's got to be greater than 1, it can't equal 1. So the three probabilities that we're interested in is these three. So this is the same as saying that find the probability that x is greater than or equal to 2, given our current scenario, because it can't go past 4, which is 0.4 plus 0.2 plus 0.1, 0.7. So the probability that Denny passes through more than 1 and less than 4 traffic lights is equal to 0.7. Okay, so that's our examples that we're going to do in class. You guys can have a crack at the practice questions that are listed in your outline. Thanks.